My name is Nadari Sichinova, and today I'll talk about algorithms, what they are, what they're used for, and why they're useful. The word algorithm comes from the word algorithmi, which is the Latin form of the name of a Persian mathematician Al-Khwarizmi. Al-Khwarizmi lived in Khwarizm region of the Persian Empire, which is currently part of Uzbekistan. He is attributed to inventing algebra and introducing Arabic numerals to the Western world. Formally, algorithms can be defined as follows. An algorithm is a self-contained, step-by-step set of unambiguous instructions to solve a specific problems. Let's take a look at examples of some of the algorithms that you might have encountered in your life. These examples include cooking recipes, pictorial instructions to reconstruct IKEA furniture, Google Maps directions to find your path from one point to another on a map, or even sheet music. For example, recipes consist of several parts that can be attributed or that can be associated with concepts known to programmers. For example, the ingredients that you use to cook something are the inputs to your algorithm. The output is what you're trying to make. In this particular example, chocolate peppermint whoopie pies. And there are even loops and termination conditions for those loops. So for example, in this case, you want to beat butter and sugar for a while until they become light and fluffy. In case of IKEA furniture assembly instructions, these instructions are pictorial, but even they include some type of loops. For example, step 4 must be repeated 3 times. In case of driving directions, you want to get from point 1 to point B. This is the problem you're trying to solve, and the directions provide you with instructions how to solve this problem. However, in this case, there is an implicit assumption that, for example, you're driving. So before you can even perform this, implement this algorithm, you have to be inside your car driving. Sheet music can be viewed as a type of algorithm. It's a set of instructions for you to produce a melody, if you can follow them directly. However, in my case, I don't play music, and therefore this is written in a language that I don't understand. So let's talk about computational algorithms that are used for computers. In case of computational algorithms, they're an unambiguous set of self-contained step-by-step instructions for computers to solve specific problems. So what about sheet music? Does it qualify? Well, it's in a language that I don't understand. Will the computer understand this language? It brings us to the following question. What languages should we use when describing algorithms? In fact, it doesn't matter what language you use. It doesn't matter if the computer understands the language. What's important is will the programmer understand what you're trying to present. So in this particular case, a programmer will use these instructions and convert them or translate them into a programming language that the computer will understand. One of the languages used for describing algorithms are flowcharts. So this is a comic that describes understanding of flowcharts, which is actually presented in a flowchart form. So in this case, the conditions are shown as rhombus. They're usually yes/no questions, so you can follow the answers, follow the paths given the yes or no answers. The boxes, they usually describe action statements that say, okay, do this or do that. And finally, the lines, the arrows, they define the control flow, what you should do, in which direction you should continue your actions. So let's take a look at an algorithm that defines that solves a problem of finding minimum, maximum, and an average of a set of some numbers. So in this particular case, when we initialize the counters sum and count to 0 and set min and max to be uninitialized. We start by reading the input. Are we at the end of the input? No. Therefore, we continue by incrementing the count variable and setting a sum to sum plus the value that we just read. We continue to the next step where we compare the number we just read to the minimum. Is it smaller than the minimum? If yes, then we update the minimum to be this number and continue. If it's not, then we skip that step. Next, we check if the number is greater than the maximum. If yes, we update the maximum to be the number we just read. If not, we skip that step. After this, we loop back to the beginning of the loop, and we read the next element. And again, we check if it's the end of the input and proceed as before. Once we reach the end of the input, the condition evaluates to yes, it is the end of the input, and we can set the average to be the ratio of the sum of all the numbers to the count of those numbers. And we can exit. We want algorithms to be as efficient as possible. Efficiency is usually defined by speed, but it also can be defined in terms of how many resources do you use. So it brings the following question. Given an algorithm, how quickly will it return the answer, in case if speed is what we care about? And the answer to this question is it depends. It depends on the size of the input, but it also depends on the values of the input. So let's take a look at a different problem. In this particular case, it's a linear search. The problem is defined as follows. We're given a sequence of numbers and a query, which is a number q, and we want to check if q is present in the sequence or not. So in this particular example, we have a sequence of numbers being 40, 21, 80, 74, 50, and the query is 85. So we want to know, does 85 occur in this sequence of numbers? Here is a flowchart that defines an algorithm, a simple algorithm of how to solve this problem. We start off by reading the first item in the list of inputs. We check, is this the end of the input? No. So then we check, is the number we just read equal to q? If yes, we can report that the item has been found and exit. If not, then we read the next item and repeat the loop. Once we reach the end of the input, this condition will evaluate to yes, and then we can exit with the answer that says the number has not been found. The query has not been found. So then the question arises, how long will it take for this algorithm to return the answer? Either item is found or item is not found, in the worst case. So in the worst case, take a minute and think about how many times will it evaluate the condition. Does the number I just read, does it equal to q or not? The correct answer is n. If for every single number, in the worst case, we will not find the number q in the list of numbers we were given as input, and it will check for every number in the sequence, does it equal to q or not. So this condition, does the number we just read equal to q or not, will be checked n times, because the input sequence consisted of n elements. Here is another question. What happens in the best case? If we're lucky, what's the smallest number of times will we check if q equals to, if the number we just read equals to q? The answer is 1. If we're very lucky, then the first number we read will be equal to q, so we'll check it once and immediately return that the item has been found. Algorithm analysis requires you to analyze an algorithm. How quickly will it return the answer you're looking for? However, it's not sufficient to count on luck on the best case scenario. So, because the users are usually impatient. We shouldn't rely on being lucky, and we also want to anticipate users' annoyance level. So in case if our algorithm happens to run really slow and the users become too annoyed, then they might not use our software anymore. Therefore, when analyzing algorithms, we look at worst case analysis. So in case of a linear search, how much time will a linear search algorithm take on an input size n in the worst case? Well, we notice that the condition, does the item equal to q, is checked n times. But we also need to count the number of times all the other operations take. For example, checking if the input, if we have reached the end of the input or not, or reading each item. So whenever we check if an item equals to Q, in the worst case, we're going to check it n times, but we will also check each time whether we reach the end of the input, and we also need to read the next item. So the total number of times that we're going to execute an operation is approximately 3n, which is 1, 2, 3 repeated n times, plus once to read the first item and once to report the answer. So the total amount of operations will be 2 plus 3n, which is approximately 3n. So as a function of the input size, the running time of this algorithm is 3n. So how fast is linear search? Can we do any better? Well, in case of Google, the problems that Google tries to solve, which is searching for documents on the web, they deal with a lot of data. There are several exabytes of data on the web these days, where 1 exabyte is 10 to the power 18 different bytes, which is approximately the number of items on the web. 10 to the 18 bytes is about 1 billion billions of bytes. How big is this? Well, assume you have a processor that runs at 1 gigahertz frequency, which means that it can process about 1 billion items per second. How long will linear search take on such large data as 1 exabyte? The answer is about 31 years. I don't think any user will be willing to wait 31 years for Google to return an answer to each query they type in the Google search bar. So how can we speed up this search? Well, if I ask you the following question, I let you pick a card from 52 playing cards, and then I ask you yes/no questions. How many questions would I need to ask you to determine which card you picked? And of course, we're looking at the worst case scenario. Take a minute and decide which of the following answers is the correct answer. The correct answer is 6. So to answer this question, I would first ask you whether the card is black or red. I can eliminate half of the cards by asking you this question, by hearing the answer to this question. Assume, let's say the card was black. Then I will decide which suit it is. Is it spades or clubs? Then I will ask you a question, is it a face card or is it a number card? And if, let's say it's a number card, then I'll ask you if it's smaller than 5 or bigger than 5. And so on and so forth until I have only one choice, and then I know which card you have. Using the same idea, we can define an algorithm for searching in the list of sorted numbers. We start by setting an active region to the whole list. Then we continue by checking the midpoint of this active region. We compare the item we're looking for to the item at the midpoint. If it's equal to that number, then we say the item is found and we are done. If it's smaller, then we set the active region to, when we check if the active region is a single item. If it's yes, then that's the only item that we needed to check, and it's not there. If the active region is more than one item, then we set the active region to be the lower half of the current region, and then we repeat the process by checking the midpoint and so on and so forth. The active region is the search space that is equivalent to, in the card example, to the set of possible cards that you might be holding in your hands. How long does binary search take if we use this approach? It seems that it's a rather difficult problem to analyze because the path within the flowchart might depend on what the input values were. However, the key observation is that the size of the active region halves with each round. So if you think about the example with playing cards, every time we reduce the possible set of cards that you might be holding in your hands by a factor of 2. How many times can we have a number n, some value n, until we get down to just 1? Well, this can be easily solved by considering the sequence of numbers that we would consider. First, we'll start with n, then we'll take a half of it, so it's n over 2, then n over 4, n over 8, up to some number that is less or equal to 1. So if we look at these numbers and we write the denominators using exponents, then it becomes n divided by 2 to the power 1, n divided by 2 to the power 2, n divided by 2 to the power 3, all the way up to n divided by 2 to the power k, for some k. If you do the matching, notice that the number of items in this sequence is equal to k, because we have one first item having a power 2 to the having a denominator 2 to the power 1. The second item has denominator 2 to the power 2. The third item has denominator 2 to the power 3, and so on. That's all we need to do is figure out what's the value k such that n divided by 2 to the power k is smaller or equal to 1. By doing a little bit of algebra, we'll find out that k has to be at least log n. So after log n iterations, our active region will be of size 1, and our algorithm will terminate. So how does it compare to linear search in practice? How fast is the binary search in practice? Well, let's say in case of playing cards, we have n, the input size of size 52. Log n is about 6. In case of the Google example, the exabyte bytes of data, log n of that is only 60. If we can do million operations per second to do the search, then we can find the item we're looking for using binary search in less than a millisecond. And that's compared to 31 years that a linear search takes. So in conclusion, algorithms is a structured approach to problem solving. They're very important in practice, and they're crucial for fast programs. An efficient algorithm can save you a lot of time. As we saw in example of searching, it can be a difference between 31 years versus 1 millisecond. And these days, big companies such as Google, Facebook, and others, they ask questions about algorithms during technical interviews. Because for them, it's important that their programs run in milliseconds rather than years. Because otherwise, their customers will be very unhappy with how long the computer takes to respond. If you want to learn more about algorithms and how to analyze them to be competitive at the job market, you should take a ICS 311 class. However, to succeed in this class, you need to take the prerequisites and be good at understanding discrete math courses, which will teach you, among other things, how to evaluate sequences that you saw in the example during binary search. This concludes this podcast on algorithms.